3 Ukrainian cruise missiles crossed into Russian airspace above the Black Sea, racing toward a gas terminal off the Krasnodar coast. An S-400 battery near Anapa, Russia's most advanced air defense, stood in their way. For the Russian operators watching their screens, it looked like another quiet morning, but they hadn't seen what was behind the Flamingos yet. A strike package designed to overwhelm, confuse, and punch through every layer of defense standing between Ukraine and those storage tanks. The Ukrainian FP-5 Flamingos flew in loose formation 200 feet above the wavetops, their composite fuselages cutting through salt air at 540 miles per hour. Each missile weighed 13,000 pounds, yet on radar they registered as something closer to a Pelican. 40 kilometers inland from the coast, roughly 20 miles northeast of the S-400 site, the Russian 91N6E Big Bird acquisition radar swept the southern horizon while its operators watched returns that didn't make sense. The phased array antenna could track 300 targets simultaneously out to 370 miles, on a good day against cooperative targets flying at altitude. These targets weren't cooperating. The operators saw ghosts. Intermittent contacts flickering through wave clutter, appearing for 2 sweeps, vanishing for 3, reappearing on a slightly different bearing each time. Something was out there. The velocity data proved that much, but the system couldn't decide what. The detection problem wasn't the radar. The detection problem was physics. At 200 feet above the water, the Earth's curvature creates a shadow that no ground-based radar can see through. The 91N6E sits on a truck chassis about 26 feet tall. Basic geometry limits the line-of-sight detection against sea-skimming targets to roughly 22 miles. The S-400's legendary 250-mile engagement range assumes high-altitude bombers cruising at 30,000 feet, not missiles hugging the wavetops where radar beams can't reach. The Flamingo's designers understood this geometry and built a weapon to exploit it. The airframe breaks down into 3 sections. The forward section, roughly 8 feet long, houses the guidance package, an inertial measurement unit containing 3 ring laser gyroscopes and 3 accelerometers, a GPS receiver with anti-jamming filters, and a mission computer that fuses navigation data and executes the pre-programmed flight path. But here is where things get interesting. The Flamingo's fuselage is built from E-glass fiberglass composite, woven glass fibers embedded in epoxy resin, layered over a honeycomb core that provides structural integrity without adding weight. This helps it defeat radar beams. At 0703 hours, the Flamingos crossed the 22-mile detection threshold. The Russian 91N6E finally achieved stable classification on the lead contact. Velocity, 541 miles per hour. Altitude, 190 feet. Heading, 047 degrees magnetic, straight toward the gas terminal, now 18 miles ahead. Profile match, cruise missile. The S-300 battery achieved classification 8 seconds later. Same target, same conclusion, redundant information that arrived too late to matter. The battery commander had maybe 50 seconds before the engagement window collapsed. The 92N6E Gravestone fire control radar slewed toward the contact, its narrower beam building the precision track needed for intercept. Behind the first Flamingo, 2 more contacts resolved into hostile tracks. Behind those, something else, slower, more numerous. Too many to count before the first missiles had to fly. He ordered engagement without waiting for the S-300 coordination. The launch sequence took 4 seconds from command to ignition. The 92N6E transmitted trajectory data to the missile's onboard computer while the launcher rail elevated to departure angle. The gas generator pressurized the ejection system, and compressed nitrogen kicked the 48N6DM clear of the tube at roughly 100 feet per second, fast enough to clear the vehicle before the solid fuel booster ignited. The 48N6DM you see flying now is a 2-stage interceptor nearly 23 feet long, weighing just under 4,000 pounds at launch. The sustainer motor ignites, and the missile begins receiving mid-course guidance updates via data link from the ground-based radar. In the terminal phase, the onboard semi-active seeker takes over. The lead 48N6DM's proximity fuse triggered 40 feet from the Flamingo. Close enough. Tungsten fragments shredded the missile's tail section, severing hydraulic lines and tumbling the airframe into the Black Sea in pieces. The second interceptor lost its lock at the worst possible moment, and the missile's onboard logic sent it into self-destruct rather than chase a solution it couldn't catch. One Flamingo down, two still inbound, their fiberglass skins soaking up radar energy like sponges. The gas terminal was now 14 miles away, less than 90 seconds of flight time. The S-300 requested handoff on the trailing contacts, but handoff required the 55K6E command post to reconcile track numbers between batteries, and reconciliation burned seconds nobody had. The data link was still negotiating when the second Flamingo crossed the 20-mile threshold. 4 more missiles launched in rapid succession, 2 from the S-400, 2 from the S-300, for 6 seconds. Both batteries were engaging the same target, their missiles converging on a single radar track that didn't know it was supposed to be gone. The S-400's interceptors arrived first. One proximity hit that gouged the Flamingo's wing root. One clean miss as the target jinked at the last moment. The S-300's missiles found a debris field where the cruise missile used to be. 2 Flamingos down, $8.4 million in interceptors expended. Both batteries screaming for reload vehicles still 4 minutes out, and the third Flamingo was already past the engagement zone, descending toward the coast at 540 miles per hour with its 2,500-pound warhead intact. Behind it, the track count on every Russian scope in the sector was still climbing. The command post display transformed in 90 seconds flat. The gas terminal was still 12 minutes from the worst of it, but the scope was chaos. Some contacts read like the Flamingos, fast, faint, flickering through clutter. Others crawled across the scope at 120 miles per hour, their radar returned steady and solid. Obviously propeller-driven, but too numerous to prioritize. Others matched nothing in the threat library, too fast for drones, too slow for cruise missiles, signatures that suggested something Russian air defense hadn't seen before. The opening salvo had been the Flamingos. The main strike was something else entirely, and the Russians were only now realizing it. But the contacts that mattered weren't the drones. They were 2 tracks now, designated Hostile 07 and Hostile 08, tracks that looked nothing like the Flamingos. These were the signatures the operators had trained to recognize since April 2022, the missiles that sank the Russian ship Moskva. These are the Long Neptune missiles, and they exist because Ukrainian engineers asked a simple question: what happens if we make it bigger? The extra space isn't for a bigger warhead, it's almost entirely fuel. The MS-400 turbofan, producing roughly 1,100 pounds of thrust, now has enough propellant to push the missile 620 miles instead of 175. The warhead did grow, from 330 pounds to 570 pounds, but only because the larger airframe could carry it without sacrificing range. The original Neptune used active radar homing, a small radar in the nose that turned on during terminal approach, found the biggest metal object against the uniform background of the sea, and guided the missile into it. So the Long Neptune deleted the radar seeker entirely. In its place, a guidance computer running 3 navigation modes simultaneously. Primary mode is GPS, receiving position updates from satellites every second. Secondary mode is inertial navigation, 3 ring laser gyroscopes measuring rotation and 3 accelerometers measuring movement. The computer integrating those measurements to track position without external input. The S-300 battery commander recognized the Neptune signature first. His operators had trained specifically on identification after Moskva. They knew what to look for. He pushed the classification up the chain while his fire control section started building solutions. But the 55K6E command post was still trying to reconcile track data between batteries, still burning seconds that neither Neptune was giving them. The Neptunes had crossed the coast near Veselovka, 40 miles southwest of the gas terminal. 2 Neptunes inbound at 560 miles per hour, definitely hostile. 14 drone contacts behind them, slower but too numerous to ignore. The S-400 had 6 missiles remaining in ready tubes. The S-300 had 8. 14 interceptors against 16 confirmed threats, and the Neptunes were the only targets that could inflict catastrophic damage in the next 90 seconds. Cruise missiles first, the battery commanders reached the same conclusion independently, their interceptors rippling off the rails within 4 seconds of each other. Hostile 07 took 3 hits and disintegrated over the coastline. Hostile 08 was luckier, or its profile was better. The Neptune jinked hard as the interceptors closed, dropping behind a low bridge near Golubitskaya at exactly the wrong moment. The 48 N6DM lost lock entirely. One detonated 50 feet away, close enough to pepper the missile's skin with fragments, but not close enough to hit it. The S-300's 48 N6E2 arrived 2 seconds later and found empty sky. Hostile 08 emerged from behind the ridge trailing debris, control surfaces chewed up but still functional. The guidance computer noted the damage, degraded roll authority, asymmetric drag, reduced maximum velocity, and recalculated everything. Terminal approach speed dropped from 560 to 490 miles per hour. The warhead didn't care. 570 pounds of high explosives works the same whether the delivery vehicle is pristine or falling apart. The Buck M3 battery commander, positioned 15 miles east of the gas terminal, had been watching tracks migrate across his scope for 4 minutes, and what he saw didn't make sense. 14 contacts inbound from the southwest, velocities reading 120 to 130 miles per hour, propeller-driven for certain. The cruise missiles had already blown through his engagement zone. He'd watched the S-400 and S-300 salvos from his display, seen icons blink out as interceptors, found targets, or went ballistic chasing ghosts. Now the strategic SAM belt was reloading, and everything else was his problem. His 9S-36 engagement radar painted the lead contacts with its phased array beam. The 9S-36 is a lighter system than the S-400's radar, roughly 900 transmit-receive modules instead of 8,500. But it's optimized for a different mission, tracking and engaging targets in the medium altitude band where cruise missiles and tactical aircraft operate. Detection range tops out at around 75 miles against fighter-sized targets. Against small drones, effective range drops to maybe 25. Classification came back: UAV. Probable type, one-way attack drone. That was the easy part. The hard part was deciding what to do about 14 of them when his battery carried 36 9M317M missiles and couldn't reload in the field. The drones, Liutyis, were nothing special to look at. Tube-launched, propeller-driven, about 12 feet long with a 22-foot wingspan that folded for transport. 75 pounds of explosive in the nose. Cheap airframe, cheap engine. Except the guidance wasn't cheap at all. The Skynode S flight computer bolted into each Liutyi's fuselage is roughly the size of a paperback novel, weighing just under 2 pounds. It contains 3 main components: a multi-core processor running navigation algorithms, an inertial measurement unit using 3-axis gyroscopes and accelerometers, and a downward-facing camera with a 60-degree field of view. 10 times per second, the camera captures a frame of the terrain below: roads, rivers, buildings, field patterns. The processor runs a visual algorithm, comparing sequential frames to estimate movement, while simultaneously matching distinctive features against a reference map loaded before launch. A road intersection here, a river bend there, a building cluster that matches stored coordinates. Each match generates a position fix accurate to within 15 feet under good conditions. When GPS is available, the Skynode fuses satellite data with visual fixes, weighting each source based on signal quality and consistency. When GPS degrades, the processor notices position jumps that don't match velocity, signal strength dropping below threshold, satellites suddenly claiming the drone teleported 600 feet in half a second. It doesn't panic. It reduces GPS confidence weighting and shifts trust toward the visual system. The drone keeps flying, keeps navigating, keeps closing in on the target. 8 miles northeast of the gas terminal, the Russian Pole 21 jammer site was doing exactly what it was designed to do. The Pole 21 is a distributed GPS denial system, not a single powerful transmitter, but a network of small jamming nodes mounted on an existing infrastructure: cell towers, utility poles, and rooftops. Each node broadcasts noise across 2 primary GPS frequencies. The nodes are synchronized to create overlapping interference patterns, denying navigation across an 80-kilometer radius while individual transmitters remain too small and too dispersed to target with anti-radiation missiles. The system worked beautifully against weapons that needed satellites to find their targets. Against drones that could navigate by looking at the ground, it was burning electricity for nothing. The Pol-21 and the Buk M3 were supposed to work as an integrated layer. Russian doctrine assumed GPS-dependent weapons would wander off course once satellite links degraded. Easier to intercept, less dangerous if they got through. The Skynode S broke that assumption. The Lutyis weren't wandering. They were navigating by terrain, holding course within 50 meters, flying straight toward the gas terminal's storage tanks. The surviving Flamingo complicated everything. It represented the highest value target on the scope. The Buk commander made his decision. Engage the cruise missile, ignore the drones. Two 9M317M interceptors roared off their rails. This missile is smaller than the S-400's 48N6DM, roughly 18 feet long, weighing 1,500 pounds, but it's faster off the rail, accelerating past Mach 4.5 in 3 seconds. The solid fuel motor burns for about 15 seconds, pushing the missile to a maximum speed near Mach 5 before burnout. Like the S-400's missile, it uses semi-active radar homing in the terminal phase, with a proximity fuse wrapped around a fragmentation warhead. The first missile arrived from above and behind, its proximity fuse triggering at 30 feet. Tungsten fragments punched through the Flamingo's tail section, shredding control surfaces and severing hydraulic lines. The cruise missile's nose pitched down, flight computer still trying to execute the programmed approach even as the airframe tumbled toward the water. It hit the Black Sea 400 yards short of the beach, its 2,500-pound warhead detonating on impact. Close, but the gas terminal survived that one. The second interceptor found only spray. 2 missiles expended, $2.2 million gone, 1 target eliminated. But the drones flew on. 34 missiles remaining, 14 drones inbound. 1 wounded Neptune that nobody had engaged since the S-300's near miss 4 minutes ago. The 9M317M was designed for aircraft and cruise missiles, not for 12-foot drones flying at 120 miles per hour. Its proximity fuse uses a small radar transmitter on the missile nose, broadcasting a continuous wave and measuring the Doppler shift of returns to detect when the target enters lethal range. The fuse triggers when return strength exceeds a threshold calibrated for aircraft-sized objects. Against a Lutyi's composite airframe, fiberglass skin over a foam core, returns were barely stronger than a large bird. Hit probability might reach 85% against a fighter, drop to less than 55% against these things. 4 9M317Ms launched in rapid sequence, 1 each for the 4 lead drones. 2 hits, 2 misses. The misses weren't guidance failures, they were fuse failures. Interceptors passing within lethal range, but not recognizing the radar return as target-like enough to detonate. 8 more missiles followed. 5 hits, 3 misses. 6 drones down. But the battery had just expended $13.2 million to destroy maybe $200,000 worth of Ukrainian hardware. And then there was the Neptune. Hostile 08 had been flying wounded for 6 minutes, trailing debris across the Krasnodar countryside, passing south of Temryuk city itself. The guidance computer had noted the damage and recalculated everything. What it was doing now, what kept the missile on course despite the fragments lodged in its control surfaces, was running a Kalman filter. The Kalman filter is a mathematical algorithm developed in 1960 that's now standard in everything from smartphone GPS to spacecraft navigation. It works by maintaining 2 parallel estimates of position, one based on GPS, one based on inertial navigation. Each estimate carries an uncertainty value, a statistical measure of how much the system trusts that particular input. Every few milliseconds, the filter compares the 2 estimates. If they agree, confidence stays high for both. If they diverge, the algorithm examines the pattern of disagreement. GPS errors from jamming have a distinctive signature: sudden, large jumps in reported position that don't correlate with measured acceleration. The satellites claim the missile teleported 600 feet northeast in half a second, but the accelerometers measured no movement. That's jamming. The filter recognizes the signature and reduces GPS confidence weighting. When the Neptune's GPS receiver started picking up Pol-21 interference, the filter noticed immediately, signal quality dropping, position estimates jumping erratically. It didn't panic. It increased INS confidence weighting, accepted the drift penalty, and kept navigating. By the time the missile crossed into the jammer's effective radius, navigation had switched almost entirely to inertial. Position accuracy was degraded, maybe 300 yards of uncertainty, but 300 yards against the gas terminal's 45-acre tank farm meant probability of impact stayed near 100%. The Neptune crossed the coast at 490 miles per hour, 300 feet off the deck, its battered airframe screaming through salt air. The Buck's engagement radar painted it, finally, but the engagement window had already collapsed. Minimum gauge for the 9M317M was about 800 yards. The Neptune would cover that distance in 3 seconds. The battery commander watched the icon cross his scope and knew there was nothing left to shoot. Hostile 08 cleared the last ridge line at 0711 hours. The gas terminal storage tanks filled the horizon. The guidance computer noted arrival at the terminal coordinates and initiated the final dive. Impact. The Neptune hit Tank 7 center mass, a 200 cubic meter pressure vessel filled with liquefied petroleum gas. The warhead punched through the half-inch steel shell and detonated inside, converting the tank from a storage vessel into a bomb. Superheated gas expanded in every direction, rupturing welds, shredding insulation, spraying flaming LPG across 4 neighboring tanks. Tank 9 went 4 seconds later. Burning fuel from Tank 7 had covered its pressure relief valve, blocking the safety mechanism that might have vented overpressure. When the steel failed, it failed all at once. A BLEV, a boiling liquid expanding vapor explosion. The fireball rose 200 feet. The Buck battery had 22 missiles remaining. 8 drones were still inbound. The Pantsir crews could see the fireball from their positions near the perimeter. And the second wave wasn't finished yet. The 8 remaining Lutyis crossed into terminal range at 0712 hours. The Pantsir batteries had 12 missiles each and maybe 40 seconds to use them. They got 4 drones, the other 4 got through. Tank 12, Tank 19, the pump hose, the transfer manifold connecting the rail yard to storage. Each 75-pound warhead was too small to rupture a pressure vessel outright, but each one started fires that spread to things fire couldn't be allowed to reach. Tank 15 went BLEV at 0715. Flame impingement from Tank 12 heating its shell past structural limits. The fireball climbed 400 feet. Tank 16 followed 90 seconds later. Then Tank 24, Tank 25, Tank 26, 3 pressure vessels rupturing within 15 seconds of each other, creating a combined fireball that satellite imagery would later measure at 600 feet across. By 0720 hours, 22 of 30 storage tanks were destroyed or burning uncontrollably. The loading rack was gone. The rail yard was gone. The fire burned for 3 days. Bye for now.